Hi, everyone. Welcome to the CIRI webinar series. For those of you who don't know, CIRI is the Critical Infrastructure Resilience Institute. It is a DHS Center of Excellence. That's a Department of Homeland Security Center of Excellence that is led by the University of Illinois at Urbana-Champaign. Today we're going to have a presentation of one of the premier research projects that's underway at CIRI. Very high visibility, very important project. Maritime ports are critical to the economy. In 2014, they contributed $4.6 trillion in value. That's a little over 25% of our gross domestic product. So maritime ports are extremely important to our economy, clearly. And they are becoming increasingly automated. In particular, to increase the number of port calls that a ship can make, right? So they want to process a ship faster so that it can get back out and bring other ships can come in. They also need to accommodate larger vessels, particularly these container ships are getting larger and larger for efficiency's sake. And so automation is very important to that. And of course, we have very tight supply chains these days. We're looking at the just-in-time inventory regime that is pretty much prevalent. And so automation is extremely important to maritime ports. And as we know, and as we've seen, maritime ports are susceptible to natural and man-made disruptions. We've seen it very obviously in the case of hurricanes. We've seen it in Texas and Florida and Louisiana, of course, just recently. And of course, we all also saw what happened in New York and New Jersey in the ports there with respect to Superstorm Sandy. But it's not just man-made and natural disasters. We've also seen disruptions caused by cyber attacks. Most recently with the NotPetya attack, which disrupted Maersk shipping in Los Angeles and Long Beach, and is estimated to be in excess of $200 million worth of damage. So the project we're going to talk about today is assessment and measurement of port disruptions. And in that project, we're going to create realistic models of maritime ports, which show the dependencies between the different infrastructure sectors, the electric, the cyber, the transportation system, and so forth. The project will model these disruptions and estimate the impact of various disruptions. And this is really important because this tool can be used by decision makers both prior to, during, and after a disruption to aid in decision making. Our presenter today is Dr. Gabriel Weaver. Gabe has a PhD from Dartmouth College and a BA in Classics and Mathematics with a minor in Computer Science from the College of Holy Cross. This project, in combination with his work as the inaugural DICAMP postdoctoral fellow here at UIUC, and in coordination with national laboratories such as Idaho National Lab and Pacific Northwest National Lab, is being used to develop a cyber-physical topology language to encode and analyze interdependencies across critical infrastructure systems. So please welcome Gabe Weaver. Thank you.
Hey, thanks a lot, Randy, for the great introduction. Really excited to be here today. This is a project that is near and dear to my heart, and hopefully we'll have a good dialogue going back and forth between it as we move forward. So just to get started, we have a great team assembled for this project, combination of both academia and industry as well. So for University of Illinois, we have Lavanya Marla. Dr. Lavanya Marla has a background in transportation and operations research. Randy, you just met, is heavily involved in the project as well, and myself. Heartland Technology is involved in developing a module, a discrete event simulation module, to actually understand the flow of commodities through the shipping port. And then RS21 is putting together some really nice advanced visualizations to develop a tool that end users, practitioners can actually use to understand disruptions. So the motivation Randy already described to some extent. It actually came a question directly from the Coast Guard and DHS, which is to understand the primary, secondary, and tertiary effects of a cascading disruption within a shipping port. And what's interesting about this is you need to understand not just the road network, but you also have rail and air and shipping networks as well. And that's just the transportation side. Then you have interdependencies with cyber. And if you're feeling especially ambitious down the road, you can start to think about power and other things as well. So it's an interesting problem because every step of the way, you have a chance to add through composition some interesting interactions. And we just want to be able to catalog those to start. But also along the way, we found that this may be relevant to U.S. Transcom as well. Transcom is responsible for moving all kinds of things across the world. And so what they're interested in, they have commercial strategic seaports, and they need to understand what the consequences of a disruption might be. And so this problem, from a variety of lenses, is relevant to a wide variety of people. So why is this important? Certainly heard a bit about this in the introduction, but there's a lot going on with shipping, and it's kind of invisible to us on a daily basis. Certainly, like when we go to a store, we see the shelves stocked, but they're stocked as a result of this just-in-time supply chain working. And a big part of that just-in-time supply chain working is shipping. So you have more than 360 sea and river ports within just the United States. And some would say there's 367 sea and river ports. But it's up for debate because we don't necessarily know the exact number. It depends on who you speak with. More than 90% of U.S. goods go through these ports. And for Syria, it's an interesting problem because shipping ports are a geographic location that's a nexus of different critical infrastructures, right? So I talked about transportation. You have all kinds of communications and IT dependencies as well, right? You have navigation, so you need your GPS to work correctly. There used to be a system called LORAN, which was a complement to that. You have the automatic identification system, so you know which ships are coming in, where they're going, and what they're carrying. Automation and logistics, the terminal operating system, is making it possible to have these larger and larger shipments come in with these larger and larger vessels to support commerce in this just-in-time supply chain. You have physical access control because you need to know who's on your port, who's on your loading dock, who's coming to pick up what. That's important. We'll get to a disruption later on where there was an issue with that. And then monitoring as well. You can either deploy people to monitor your border for physical security, right? Or you can actually deploy security cameras to look at the perimeter of the port. And that's also another system that we're layering in there. So there's additional levels of complexity being added for various purposes, whether it's security or for automation. Transportation sector I already alluded to, but you have an intermodal system, complicated road, rail, air, vessel, just to support this supply chain. And then the energy sector fits in there as well, right? Because you certainly need diesel to be able to operate a lot of these vehicles within the port, just locally. A lot of these tanker vessels will come in bringing jet fuel, and the jet fuel will make its way down to airports. And you need airports to have fuel in order to continue working. You need some of these fuels as well for electrical power. So there's all kinds of interesting interactions. And you see that in the diagram on the right? So we really need to be able to understand these dependencies to identify, evaluate, and mitigate risks to the Maritime Transportation System, or MTS. So on the diagram on the right, you can see there's different layers that we can add on. There's a wide variety of critical infrastructure sectors, right? But we're primarily focusing actually on transportation and cyber. Now, if you take into account some previous research and projects like CREDC as well, U of I is well positioned to talk about interactions with power systems as well. So then the trick is, how do you compose, based upon these interactions that you discover, your transportation system and your communications and IT systems. And people really need to understand this in order to evaluate risk and then make appropriate mitigations so that they can recover. So communications and IT, the U.S. Coast Guard in 2015 published a cyber strategy, and it brought it to the forefront the need to have a good cohesive approach to not just physical security, but computer security as well. The transportation sector, you have this symbiotic relationship between ports, and then the energy sector, you need electrical power and things like diesel, right? So I just talked about that. But we really need to be able to model the port as a system, And keep in the back of our head that it's kind of an open world. There may be interactions that we're not accounting for, but we need to be able to extend the framework so that we can account for them as best we can. And the MTSA, or the Maritime Transportation Security Act, actually requires stakeholders to understand and mitigate these risks, right? So there's area maritime security committees, and they are local to specific ports, but they're also regional. So for example, we're working with Port Everglades. I'll get more into that later. They have to have a security policy or security plan for different kinds of disruptions that can occur. But at the same time, they need to coordinate that both with the tenants in their port, so companies like Crowley, for example, companies like Citgo on the petroleum side. But then they also have to be able to coordinate up at a regional level with Sector Miami. And Sector Miami includes, I don't know, maybe 10 different ports, I'd say. There's a variety of different stakeholders as a result, ranging from the captain of the port, who determines whether or not a port can reopen after a disaster, among other things, to people involved in finance and business, port tenants, whether it's cargo, petroleum, or cruise. You even have individual people, right, going on vacation, going through the port. That poses an access control problem, potentially, depending who's going through there. And so there's a variety of existing approaches to manage and mitigate these risks, and we want to not just invent something that doesn't respect that, because there's a lot of expertise cooked into these already. So the Maritime Security Risk Analysis Model, the MISRAM, is out of the Coast Guard. They look more at physical security, but they're increasingly integrating more cyber, and that's where our project overlaps quite a bit. Through the NIST cybersecurity framework, for example, that provides a cohesive set of uniform controls that map into the NIST 800 framework as well. And so, maybe by combining those two, we can get a handle at these hybrid kind of risk assessments. Hybrid in the sense that you're not just considering cyber or transportation in isolation. You're not just considering the threats from one domain in isolation, but you're able to integrate them and understand how their interactions work. So this is a big kind of pile of spaghetti in some sense. And so what we're trying to do is build a general software framework to model specific ports, identify risks, and evaluate mitigations. So Coast Guard will say, oh, if you've seen a port and you know a port, then you know one port. And science is like, well, we want to produce knowledge that can generalize. And so it's an interesting research question, right? You have practitioners that have very specific kinds of constraints to their ports, but at the same time, you want to produce research that produces a generalizable result, or at least you can run the same kinds of procedures again and again. And so what we basically do is we'll break it down into the milestones of the first part of the grant. We want to be able to baseline operations, so understand how do ports even operate from the top down. Like if you take a port and you kind of parachute in or fly in, if you're not up for parachuting, you can decompose it and understand the different components of each one. We want to also be able to catalog disruptions. Now, our emphasis was not on physical, but certainly physical is a major concern to the port that we worked with, Port Everglades, because they have hurricanes, right? And so you need to be able to accommodate not just physical disruptions, but also disruptions from all these automation systems, and as well as security systems being layered on, or cyber, as we like to say. And then simulate cascading effects. So how does one disruption percolate through the entire port system? Or how does it start? How does the latency in a computer network percolate to the flow of containers through the shipping port? These are the kinds of questions we want to be able to model, and we have some different approaches for that. And finally, once you understand the flow of commodities through that system, we want to be able to get a handle on what are the economic impacts of that. And so that's kind of the blueprint for our research up to this point. And the value is researchers and stakeholders can conduct different what-if analyses. So instead of thinking in our head, like what would happen if, and then you have a discussion, and that's really good and useful, but there's so many interactions now, it's really hard for a human to keep all of them, even as a group, in their head. And so we want this tool to be able to simulate various disruptions. Left of boom, left of something happening. This is good for exercises, training exercises, and planning. During boom, if your computer network is still up, or if you can still use the computer, you can think about mitigations. And then right of boom as well, you want to be able to evaluate response and recovery strategies. and strategies to not just build it back to functional, but build it back better than it was before. If you're going to have to rebuild it, some people say that that's what you should do. So that's where we're coming from in terms of the value, because what's interesting about this is it's kind of a problem where you're doing research, but you also want practical impact. So objectives. Analyses have to be conducted continually because your environment is continually evolving. You have, for example, weather. Weather patterns are evolving quite a bit, and you have, as a result, more storm surge and flood. You also have intelligent adversaries whose tactics and procedures may be changing as well. So you want to be able to kind of think through, how does the system respond as these different disruptions evolve? And it needs to be a robust set of repeatable analyses by which you can perform what-if analyses. Why? Because people will be making decisions based upon the tool. So you want to be sure that your stuff is grounded in something that's repeatable. And just that alone is something that is a research item, although not direct the research we're pursuing. This is a research item in terms of reproducibility of research results. And we work with sensitive, we want to be able to work with sensitive and non-sensitive data. We're working in the non-sensitive data portion of that. So here's an outline for today. We've already been through the introduction, the motivation. We're going to talk about the objectives in terms of the baseline operations, the field work we've done, the cyber physical disruptions catalog. That's a work in progress that's being added to, but essentially we'll be able to catalog the different types of disruptions that can occur, so then we can start to think about composing those disruptions over time and understanding these hybrid disruptions. Simulate cascading disruptions. So if you introduce a sequence of disruptions or a single disruption to the network, how does that affect your commodity flow? How does that affect your commodity flow not just at the port, but more at a broader regional level as well? Depending who your stakeholder is, you might have someone that's only concerned about the port, or you may have someone that's interested, like DHS, at the whole regional level as well. And then advanced visualizations is the next thing we're going to get to. So first, part of the research, because it's so applied, it's important to break out of the ivory tower, right? And make sure that your assumptions are really what are valid. So we went to Port Everglades, Florida, and this is a very quick video. It's 30 seconds, but you get the idea. You have vessels coming in. They're offloaded by a gantry crane, which we'll see here. Gantry cranes use not just electricity, but a variety of things that we'll get into more detail about. They're then transported to the container yard, where if they're refrigerated, they may dwell for less time than something that's not refrigerated. There's also requirements for refrigerated cargo. Any cargo leaving by truck has to be scanned at these radiation portals, but you also have the option of air, because you're in Port Everglades, and rail, so you have that intermodal kind of aspect. As a result, it's a really interesting port to work with, to start with. It's the #1 seaport in Florida by revenue, so it's not a toy problem. It's legitimately important port for the operations of not just revenue, but for container. It's the #1 container port in Florida. It's the #1 refrigerated cargo port. It's kind of where we start to interact with Latin America and trade coming out of Latin America. This is an important port for that. Nearly all the gasoline in southern Florida comes through this port. All the jet fuel from Miami International Airport comes through this port. It also set the world record several times in terms of number of people for crews that go through the shipping port. And that's interesting from an access control perspective. And you can think about various disruptions where you have lots of people and you need to be able to have a plan for that. So it's interesting for a variety of reasons. What we focused on, we didn't focus on crews, because we're focused more on the petroleum operations and container operations. So what's neat about Port Everglades is they have North Port and South Port, and it's very crisp and clean in terms of what occurs where. There's a single road, more or less, there's a single road that connects North Port to South Port. So depending if that is disrupted, that may be an issue, but there are other roads as well, just not the primary one. So let's delve in and check out these operations. We got a tour from a guy from Crowley. Crowley is a terminal operator here, and he walked us through in half an afternoon and explained to us the flow of different containers through the system. So you're coming in as a truck, and you have this shared resource of a road. And you had to be able to get into the correct lane to get into the right terminal operator. So if you're Crowley, maybe you get into the rightmost lane. If you're King Ocean, maybe you get into the second to the rightmost lane. That's not always an option, however, because people take lunch at different times. So you may have a backup. This is a small example of a cascade. If you have a backup of trucks, so, once upon a time the road used to run over the rail, and so you have a contention between your railroad and your vehicles going across. So just on the transportation level, you have some interesting cascading effects. But anyway, I'm babbling. The truck lane, trucks come to pick up goods in line, and then they make their way to the gate. At the gate, trucks are checked to be sure they're at the right place at the right time. That's very general, right? But you need to know who you are. Is the driver who you think it is? What are they coming to pick up or drop off, for that matter? Is all their paperwork in order? Have they even made a gate appointment? Because if you're shipping stuff out for export, you need to make a gate appointment. All this stuff is tied into something we call later the terminal operating system. And now if someone checks out and it makes sense, they can go to the container yard and pick up the container. If not, however, they end up in a kind of a limbo situation where they have to wait until the correct paperwork is actually through. And for truck drivers, time is money, so you don't want that to happen. There are ways around that, though, and maybe some of you have heard of the disruption, but we'll talk about it later. Container yard. Containers are full of cargo. They're in these standardized units called TEUs. It can be full of all kinds of things, which makes it interesting from a research perspective as well. In terms of us, we're looking at retail and things like bananas coming up from South America. Those have the most economic impact for Port Everglades. Certainly, it's extensible to other types of commodities as well. One thing that's interesting about bananas, the dwell times have to be shorter because they're refrigerated, right? And you also need electricity for that to work. Gantry cranes, they're large, and they're only going to get larger as the ships get larger. So for Port Everglades in particular, these cranes are going to stay the way they are, but there's going to be more cranes put in over here, and they're going to be, I think, post-Panamax. They're going to be very tall. And because they're so tall, here's another interaction that you may not think about if you're just in a tabletop, but you want to encode. Because they're so tall, you have interactions with the FAA. You have to get permission for the airplanes to be able to fly or to be able to construct a structure that high. So it's interesting in that sense as well. They load and unload cargo. And then the seaway. Ships move in and out of the seaway to bring goods into and out of the port. And how the seaway is constructed is also a potential source for disruption. Are there multiple ways in and out of the port? Is there one way out of the port? How wide is the seaway? If some vessels are docked, can another vessel that needs to get out, or does it have to wait for all the others to leave? Is it just a commercial seaway, or do you also have people who can go recreationally? So there's things that need to be considered in terms of risk assessment. If you look at kind of beneath the surface, this is for engineering open house. This is a little cartoon of the kinds of interactions you can get between your communications and IT systems and your container operations. You have the automatic identification system, the AIS, that's used to identify ships as they come into port. When I was in Germany, there was a gentleman who was actually involved in hacking and talking about different kinds of hacks on that system. But he did a responsible disclosure, so it's fine. But you can imagine this is tied into who you are and where you're going. And that's important because you have pilots within the ports that need to hop into these vessels and dock them because port pilots know the port better. Gantry cranes. Gantry cranes are not just cranes anymore. They're becoming automated. Some are eliminating the human altogether. But at Port Everglades, that's not the case. But they still use technologies like optical character recognition, OCR, or RFID to be able to identify your container, right? So if you have an issue with one of those systems, you may not correctly identify your container. That could be a problem. Or it could be a benefit if you're trafficking drugs and trying to use the infrastructure for your own benefit, which has happened. Container yard, the terminal operating system. You want to be able to orchestrate the movement of different containers through the port. there's a lot of different pieces. So if you're unloading containers from a vessel, you get assigned, you have a crew that's assigned to you basically, and that crew has a view of just the containers in that vessel. It orchestrates all the movements as well as one that gets picked up. And the gate operating system as well, we talked about that earlier, but basically says, are you allowed to go through the gate or not at this time period, and can you pick up or not? So that, part of our research is going on these expeditions, or that glorifies it too much, on these trips, right, to do field work, and then we construct some simple graph-based models and increasingly more complex graph-based models to just understand these different interactions and the flow of commodities through the network. So here you can see export. If I want to ship something, I can move it out over a highway. You go to the gate, and it's just the slide I showed you before, except in a graph-based kind of flow format, right? And there's a reason for that. And then I have different cyber touch points where I have interdependencies between different services that are provided and the different components of the transportation network. Now, just this this fits fine on a slide, but you can imagine if you blow these out into a more detailed kind of model where you have actual devices instead of just services being on and off, it gets more complicated. Right now, we're focusing mainly on doing a good job on this transportation network with just the cyber touch points, but this is a place where we could expand that, and you can get actual latencies going through the system and understand how do actual latencies affect things like your container targeting system, for example, where you need to inspect containers. So petroleum operations, much the same story. You have a petroleum pier. Tankers are coming in, carrying gasoline, jet fuel, and other bulk liquids that dock at the terminal. Products are pumped through the manifold and stored in these large tanks. The trucks move through the access gate to the fuel load racks. The way this stuff gets out of here is by pipeline or by truck. Now, the one thing to consider is as your vessels get larger and larger, you can get the stuff into the port, but can you get it out of the port efficiently? Can your transportation system hold up? Can you expand that enough so the trucks can go? That's something interesting to consider. And then at the load rack, trucks get the right blended amount of gasoline. Why is that important? Because every single kind of gasoline provider has their own blend of chemicals that they'll add additives. And so, I don't know, like a Chevron is different from a Citgo in terms of those additives. Moreover, there's a blending of ethanol along with the gasoline to bring it up from 85 octane to 87 octane. And if you can't blend it correctly, you're not going to have gasoline that you can actually use. Or if you have a shortage of ethanol, you're not going to have gasoline you can actually use. The access road is important because that's how you get off the port. And then the pipeline, like I said, that transports jet fuel from tanks to the surrounding airports. And so there's a cascading effect if there ever was one, right? Or if you have a disruption to your pipeline, you're only as good as your reserves at your airport at that point. But then there's also the chance to mess with what's actually going through the pipes too. So petroleum operations beneath the surface, what you can't see. So here's a representative, artificial but realistic manifold beneath the that would go through Port Everglades. Port Everglades is interesting because they share one manifold, and through different valves, you can route it to different tanks. So that's a shared resource again, right? So there's the potential for more impact if a disruption occurs. Vessels will come in to the pier, and you need radios by law. The Coast Guard has it such that you need radio communication between people on the dock and on the ship. Why? Because you're dealing with something that's potentially really volatile, and you need to make sure that even things like your vapor pressure and the kind of product, the rate at which you're pumping it, it all lines up from the ship to the tanks. So if the radio communications are down, you can't do it. The remote terminal units are used to monitor leak gauges and also detect leaks as well. So you have a lot of tanks. You can't just go out there and manually look, right? So you need to have some kind of RTU to tell you, what's the state of my tank. It's really important too before a hurricane. If you drain your tank too low, these tanks will actually have the potential to blow off of the concrete because they're too light. So you need to keep enough fuel in your tank so that they don't blow away. So the ability to monitor your tanks is very important. And then PLCs are used to monitor truck weight and the blend of the fuel, like we were talking about before, and that's tied to proprietary kinds of additives that are added as well. Programmable logic controllers control access through the gates. They're very specific, so it's not as likely that anyone would target that per se, but the potential is there. It's an automated system. And then the pipeline. They're tied into pipeline meters and pumps, and these pipelines are too long to just manually walk. They're walked once in a while, so you're dependent upon that. And just so you know, there's also rail, which we're not going to go into too much detail at all, but there's a railway that we also visited. We're not modeling that yet, but we have the flow diagrams in place that. So you have the cyber network, and these are the different kinds of services. So you have things like radio that are tied to your vessel and your pier. There's dependencies there. And you have this diagram here of the transportation system. So you have tankers coming in via ocean to a pier. They go to different types of tanks for different commodities, whether it's jet fuel, gasoline, or ethanol. You also have train. The Florida East Coast Railway brings in ethanol to a certain terminal, and then it gets stored there, and you need that in order to even get your gasoline out of there. And then you have highway, and these all make their way to southern Florida or different airports. So here's a toy contrived example, but nonetheless it'll illustrate a point. Very unlikely that you'll have an attacker just sitting out there looking to jam radio one day, because it's not going to have a big enough economic impact to cause a whole lot of problems. But anyway, let's say the radio goes down. That impacts your ability to offload product, and so the person at the pier can no longer communicate with the person on the ship. That's going to affect your service time or your latency at that pier, which will then cascade and affect, depending on reserves and how long this would last, which is why it's contrived, but it illustrates a point. It'll affect your availability of jet fuel at places like airports. And then depending upon the time of year, which is important, as well as the type of commodity being pushed through the pipes, it'll affect your economic impact. If it's a busy time of year, then it could be a lot worse to have a disruption than at a slower time of year. So that kind of gives you the framework for just the field work that we did. So methodology, we go out in the field, we make sure that we understand the basic flow of different types of commodities and the assets involved at a high level, and the interdependencies, the cyber touch points. And then we talk about cyber physical disruptions. This is an ongoing work in progress, but here's a snippet of it. So we're actually working both with the Coast Guard on this as well as Transcom to develop a nice model that you could then use to describe hybrid disruptions. So you want to catalog theoretically possible disruptions to the transportation system. And it's different because you don't need to actually develop any kind of disruption. You just need to be able to quantify what you think an effect of such a disruption would be. And so this allows you to then kind of brainstorm things that you may not otherwise. And also allows you to prioritize disruptions, because if you have a good model of how commodities flow through the network, when you perturb things like service time and capacity, then you can get a feel for what the economic impact might be and prioritize and rank according to that. So here are some examples. Maersk, ransomware, depending who you believe, it came in through one of the accounting systems, through a VPN, and then it propagated. It lasted for about 10 days, and I have it down here. There are like 4,000 servers and 45,000 PCs that had to be reinstalled from scratch in the period of 10 days, which is, according to the media, it's a Herculean effort, right, to be able to do something like that. Lots of money was lost, but it wasn't true ransomware according to Kaspersky. I don't know if you believe Kaspersky or not, but it's just like it had no ties to a crypto wallet, so it would just erase and scramble. You could never actually decode. And so this is interesting, right? Because it's masquerading as something, or maybe it's just easier to modify the code a little bit, and then you wouldn't be able to get your data back anyway. The terminal operating system. So this is another, I like this story because it's an interesting combination. So the Port of Antwerp, I believe this started in 2011. It lasted through 2013. So you get spam, you get phishing attacks, right? And so people actually in Port of Antwerp were victims to a phishing attack. And then they discovered this and they fixed it. And then the criminal organization decided we need to still be able to get our drugs through the port. And so what we're going to do is we're going to go in and physically break into the offices and install key loggers. And so that's what they did. They put together some key loggers. As a result, they were able to get passwords and modify the terminal operating system. Terminal operating system is like any other operating system in the sense that just as we keep track of files, this thing's keeping track of containers. So if you're trying to smuggle drugs, you can just edit that database, right? And then you can say, oh, don't worry, you don't need to inspect that, or that container is really over here. And then they had their own drivers with all the correct credentials go in and pick up the container. Right, so it's an interesting combination. It's an interesting hybrid disruption or attack in the sense that you have people trying to do the easy thing first, escalating to do something physical, right, and breaking in and installing key loggers, and then just doing what they need to do with the terminal operating system to be able to get stuff out. Now, the way they were found wasn't through any kind of monitoring or anything like that. It was found because the person who was coming to pick up the original shipment actually came a little bit early, and he ended up getting shot. There's details in there I need to be a little more precise with, but it's worth a read. But they were discovered because the truck driver who was doing the job he was supposed to got shot, and that's how they caught the criminals in this case. So it's an interesting kind of disruption. Now, how could you model that? You could think about availability of terminal operation, right? A terminal operating system, and that'll affect things like your service time for sure. You can also then think about how do you alter the integrity of those different entries within the terminal operating system. And if you can simulate at the level of a container, you can start to do things like that. So let's talk about simulating cascading disruptions and the movement of containers. So what's our model? We want to be grounded in the real world, so we're going out and doing field work to build up network descriptions that reflect what we see. We're getting that validated, or the thumbs up from Coast Guard and people at Transcom and actual port tenants as well. We have shipments. We have something called piers, which it gives you the bills of lading for different vessels. You have vessel schedules as well available, so you can understand the rate at which ships go in and out of a port at different terminals. And then we have disruptions, which we were just talking about, right? And there's actually a recent FireEye report with even more interesting kinds of disruptions, where you're talking about things that are compromising remote desktop protocol. So you can imagine, you could see what the busy times are and then plan accordingly. We also have this optimal network flow module, which given a disruption, it's a optimal multi-commodity network flow problem. So we all remember network flow back in the day, right? You just have one commodity and it's going through a network from a source to a target, and you have capacities and it's great. Now you have more commodities and it gets a lot more complicated. And that's what Dr. Marla is helping us develop, is this optimal network flow algorithm that can take into account, given a disruption, how should we reroute the commodities and what's the impact? And then we can feed these different paths that the commodities should traverse through the port into a discrete event simulation, right? And those paths may change over time depending upon how busy different routes get. And the discrete event simulation has different events. One of them is the arrival of a commodity at the dock, and also like when the commodities leave different nodes within the shipping port. And as a result, we're able to build up an idea of the flow of commodities through the system. Some of the functionality here actually overlaps, which allows us to then evaluate why do they differ. And there's also various approaches to other Siri projects that are being pursued. And one really cool thing is maybe we could actually compare our results at some point, because we're lined up according to our network description. So we can run the same kind of flows using different approaches. And then visualizations, advanced visualizations. So discrete event simulation functionality. It's a queuing model at a high level. There's more details when you actually code in the guts, but at a high level, you have a queuing model, right? So you have a queue which is bounded. This is the number of things that can wait in line to be serviced at a pier. You have a rate of arrivals, which you can get at from schedules, from vessel schedules. You also have an idea of what the ratio is, like TEUs per vessel. And then you can have a service time at all these. And then you mix in things like where are the cyber touch points, and then if there is a latency here, how does this affect the service time at the gate? And being a good academic, this is the hand-wavy part, right? Because this is where you need to interact with practitioners to understand what would be reasonable functions from here to here. Is it even reasonable to talk about this? But the idea is actually to help support people to make decisions. And so this is a good cut at that. You have accumulated costs, so as you move through different paths on the network, it may cost more or less, but some things may actually take more time, so you have different notions of cost as well. And so here's a use case of that where we're at Port Everglades. We just do a very simple example. 7 shipments over 1 week. You have a different number of grocery and retail going through it, and a cyber attack disables one of the gates, so you have more latency at the gate. So here you have a vessel that comes in at a pier. Containers then flow into a container yard. This is Crowley. From there, they can go out via truck. The arcs aren't geocoded. They can go out via truck on the road to a gate and then out the highway to southern or western Florida. However, if you're a container that needs to be targeted, you can flow up here to an inspection facility, and there may be 1 or more inspection facilities you have to go through, and that affects your flow through the network. And so here's a simple simulation where you can see this is number of containers at this particular node. This is the crane, makes its way into the container yard. And you'll see that clearly we need to get more realistic data in here, but nonetheless, we need to validate, but we're just working on making sure the code works correctly first. And it's moving through the network. And this is good because now you can actually tweak these different model parameters like service time and capacity and understand what the effects are. So for someone who's interested in just the port, that's good. But if you're interested in a more regional perspective, let's say you're not just Port Everglades, you're sector Miami, you want to be able to understand what the regional impact is as well. So that's where you start treating each port as a node in and of itself in this broader regional network. And then you start to think about down the line, okay, well, if I have multiple ports, can I start to understand dependencies on multiple ports? And you have a sense of that in the economic data. So disruption effects on retail. Here's a simple example, but you get the idea. You could present this very simple chart and show that, given a disruption, all your commodities in the undisrupted case make its way through to its destination, but it's lagging in the case of a disruption. You can play out different kinds of disruptions. We can change the models for the disruptions and understand. Now we're going to go into optimal network flow. I'll just briefly discuss it. So I was telling you before about how it's a lot like just your traditional network flow, except it's multiple commodities. You have sources and destinations, but there's an interesting wrinkle in this as well, because we're also starting to talk about vehicles. So there's a limited number of vehicles in your container yard, and that may vary as well if diesel's available. So there's some cool side effects here. Depending on the number of vehicles that are available, that'll affect your ability to move containers throughout your port. And so we're not just modeling sources and destinations of commodities, but also availability and capacities of vehicles as well. And that's pretty neat because we're talking to Ports of Auckland. Ports of Auckland is doing a brownfield they're actually migrating as the port is running to an automated system, a system of automated straddles combined with human-operated straddles. And so that's interesting, right? So we're looking through different disruption cases where your automated straddles might be inoperable, or they might be degraded in some way, or a certain number of them might be. And then how does that impact your ability to recover? Some straddles they're building them now where they don't even have seats for them. Right, so if something were to happen to one of these straddles, not at Ports of Auckland, but they're manufacturing straddles which move containers in your container yard without any seats. So how do you recover from that? You'd have to bring in some other kind of straddle. And do you even have the labor to do that at that point, right? Because maybe you employ fewer people that have that skill because of the automation. So it's something interesting to consider. There's different constraints, so minimize travel costs and delay costs. Vehicles have starting and ending positions. Eventually we want to be able to have them so that they can loop through because that's more realistic. There's different types of commodities and there's a capacity on the vehicles. So it's a fun kind of alternative approach to discrete event simulation. And then through being able to compare those results, maybe we'll see some interesting things and learn more. So advanced visualizations, the idea for the practitioner is to interact with a cloud-based application. And so they're going to be able to log in and start to access the tool. And if they're interested in container operations, they can see the schedule of vehicles that's coming in. You could actually pull that in from real vessel schedules. And they can see what the maritime security level is, what the condition of the port is, and then for some disruption, what the duration is. So both the disruption and the duration. These are just wireframes. We're actually mapping the output of the discrete event simulation and ONF into an interface like this right now. So just so you know, if you notice any knobs in there that don't quite line up with the model, that's why. This is work in progress. The maritime security level will adjust how long it takes to get through a gate. There's other security precautions that are deployed. As a result, it may take longer to get commodities in and out of the port. The condition of the port is important because that alters with your weather. So the Coast Guard was saying if there's a hurricane, that'll alter, the availability of how high you can actually stack your containers. And so your containers, once a storm gets close enough, you can be no more than 3 containers high, but in good conditions, you like to maybe be able to stack them higher to make better use of the real estate. So that's an interesting thing you consider. And then the disruption duration that we were asked again and again, what kind of duration of disruption should you consider? That's a good question because it really depends upon who you're targeting this tool to be used by, right? So if you're talking about a port operator or someone that's a port tenant, they want to know about these more short-term disruptions. So like if you have an oil spill that connects north to south port, that's going to affect them. But someone like a larger organization like Sector Miami probably doesn't really care about that. They care more about longer-term, larger disruptions. And so the answer is we need to be able to accommodate both. And so that's why you have this parameter here, disruption duration. You need to be able to hook in disruptions not just to the physical, but to the cyber as well. And so we have these blue kind of orbs for physical assets. And then wherever there's a cyber touch point, we have these pink orbs. And during the simulation, these can grow larger or smaller to indicate severity of the disruption over time. So that then users have a visual interface to where things are affected. And again, you will want to understand economic impact, not just functional impact. And so you want to be able to just have a calculator that says, given this disruption, we understand the effect on the flow of commodities, what's the overall cost? And again, this is a wireframe. These numbers don't quite add up if you look carefully, but they will. So economic impact of cyber disruptions is something that we're exploring in more depth. First, we just need to understand how the port operates. Then we need to validate our models. And now, once we get that, we can do some very simple things to help people make decisions. So one is you understand the value of commodities per unit, and you can just do a simple multiplication exercises. But that's not really, that's useful and practical, but it's not very interesting from a research perspective. So from a research perspective, there's more sophisticated models out there. There's like an input-output model, which will give you a more pessimistic kind of estimate of what your losses would be. And there's been work done on that. So things like dirty bomb attacks have been modeled at a regional level. There's another study that coupled a transportation network like the one I showed you for container operations with an input-output model and was able to understand how commodities that are output were affected by perturbing that network. So it's kind of interesting. But then there's also, I'd be remiss if I didn't mention related Siri projects to this very question. One, how do you know which kinds of disruptions are relevant? Maybe you can actually use data from insurance claims. And so if you look at Dr. Keeson's work with CPAR, he's looking at insurance claims, cyber insurance claims per different sectors. And you can get some data then on, what are the most common kinds of disruptions that are reported, maybe they're not always reported, versus what are the average losses. And you can see that those two are not always the same. So here you have malicious data breach. It happens a lot, but it has less impact than IT processing errors that happens a little, but has a big impact in terms of dollars, average losses anyway. So that's interesting. The other is Dr. Adam Rose. He's working on something besides an input-output model for disruptions. And that's also worth considering because he's done some modeling of economic disruptions to ports. So the goal is to have this higher, more detailed, higher fidelity kind of model coupled up with some nice economic models to be able to help people support decisions. And so just to conclude, the shipping ports and seaports are vital to our economy. They're a nexus of critical infrastructure. Stakeholders really need a common operating picture. And I know that's a buzzword, but it's true. There's too much to keep inside our heads at this point, and we're definitely dependent upon these automation technologies. So our only choice then is to depend upon technology further to understand our own environment. And that's a whole conversation in and of itself. So we're creating a framework to model actual port operations and to simulate cascading disruptions. And we want to build a theoretically sound tool, of course, because we're researchers, but we want it to have practical impact as well. And so I just want to say thank you, and these are some of our collaborators. And at this point, I'll take any questions.
What's interesting is that you're using some of the same mathematical concept and theory applied to communication networks and applying them to physical objects. Was that where a lot of the concepts came from?
No, so actually, a lot of the early work came out of looking at electrical power. And so we were looking at kind of cyber-physical interactions on the electrical power side.
I see. Because when you use terms,
that's a good point.
When you use terms like nodes, that makes you think of computers.
Yeah. So it's like really nice. Is a graph is a very flexible way to represent all kinds of interconnections and objects, really data structures. So it's a good place to start, and you can validate these different constructs and maybe start to get a language so that you can run multiple algorithms on the same kinds of things at some level.
Very interesting research. I see the opportunity, example for power system to quantify the cost of a blackout. At this time, it looks like to me that the research is mostly a chain supply problem, in the sense that you have in, you have out, you have a number of the nodes, and you consider at the same time, for whatever reason, a node is not working. What is the cost? What are the consequences? So I will advise maybe in the future, you can focus on cyber impact, try to connect better the cyber impact within all the chain supply and quantify how this will affect all the chain. So this was my contribution.
Good. Oh, thanks. So just so you know, we're like the cyber model is just understanding at this point where the touch points are, and getting something more interesting in terms of an actual network is kind of a next step. But for power as well, there's some interesting stuff that could be done. So in general, the hunch, it's not very scientific to say you have a hunch, but the hunch is maybe you can couple these graph-based models with simulations, and then you start to do co-simulation, which has been done, but that's hard enough. But maybe there's a chance to look at interactions between multiple sectors. And we have simulators for transportation. We have simulators for cyber as well, right? Beyond the one we're developing, there's also some stuff done with Omnet. We have it for power. So then maybe there's some interesting research there. Because co-simulation with more than two things is, at least according to one survey paper out of Cornell in 2017, that's new. That's a hard one. So. Yep.
I'm assuming each maritime port is different in their infrastructure. So I know you're working in modeling and validating one specific port. So how do you go about modeling and validating the other ports in sizes, or depending on if they're next to a river, lake, taking in the different factors?
Right. So it's an interesting question because we started out with Port Everglades just to get an idea for the line. It was small enough socially it was much better to interact. So we're not ready for something like a Port of LA or Long Beach, but we are talking with ports of Auckland And Ports of Auckland is a completely different type of shipping port in the sense that they have more automation technology. And so it's not as easy to compare that to like a Port Everglades.
Okay.
So that's how we're starting to test how well does this generalize.
Okay, but so how do you like model it for other ports? You know, eventually you want to incorporate what you have found here into other ports.
Right.
So how do you roll it out on a large scale, you know, after validating certain different ports?
Right, so right now we're just doing a small prototype proof of concept. With that said, so there is some work that I'm speaking with someone about. There's Hui Trong, who does graph motifs.
Okay.
And so if we build up enough of an understanding of the type of interactions, interdependencies, you might be able to do stuff through graph grammars to generate larger scale synthetic data sets.
Okay.
And that could be a lot of fun. And if you have the ability to generate graphs, there's a lot of ifs, right? But then you could load that into your simulation because you're using that common language. You have a shot at something that would scale up more. So if that's it, just thanks for your time.